So the input to a queuing system is the arrival process when customers come into the system. And then the output of the queuing system is the service process. So customer gets out from the system when they have finished with what they need from the system. And in this video, I'm going to talk about how we are going to model those processes. We will start by modeling the arrival process. And we've got an assumption for the arrivals that is no more than one arrival can occur at a given instant. So at a particular time, at most, only one arrival can happen. At most, only one customer can appear at a given instant. Okay, so let's take a look at an illustration here. So let's say we have this timeline here, and then we have the first customer appears at t equals 3 because she is the first customer, so we will denote this by t1 equals 3. So this is the time that the first customer arrived. Let's say the time that the second customer arrived is at t2 equals 8, and then t3 equals 15 means that the third customer arrives at the time 15. Now, usually in queuing theory, we are not very interested in the time point where a customer arrives. Instead, we are much more interested at the inter-arrival time. So inter-arrival time is the time between the arrivals of two customers. Okay, so here we have the inter-arrival time between the second customer and the first customer equals 5. And then the inter-arrival between the third and the second customers equals 7 because the third customer appears at the time 15, the second appears at time 8, so the inter-arrival times between them is 7. There's an assumption for the inter-arrival time, which is that these inter-arrival times, they are independent continuous random variables described by A. Independent means that these inter-arrival times, they do not affect one another. The information of one inter-arrival time does not tell us anything about the others. And these random variables, they are governed by a distribution. And the distribution of this inter-arrival time is assumed to be independent of the time of the day or the day of the week, which means that the distribution of inter-arrival times is assumed to be the same whether it is in the midnight, afternoon, evening, or whether it is weekdays or workdays. The distribution of these inter-arrival times is assumed to be the same. So because the inter-arrival time is a random variable, we are going to have a probability density function to describe that random variable. The most common choice is exponential distribution, which has the parameter lambda. Now, this is how exponential distributions PDF looks like. And then this is the graph. And then based on this, suppose we would like to find out the probability that the interval time is less than c, then we take the integral from 0 up to c, and then here is the probability density function of the exponential distribution. Suppose we would like to find out the probability that the inter-arrival time is greater than c, then we take the integral between z and infinity. Now this exponential distribution has the parameter lambda, and in the context of queuing theory, lambda is the arrival rate. And then the unit for this arrival rate is customers per hour. So the number of customers per unit of time. This is the average inter-arrival time, 1 over lambda. And then the unit for average inter-arrival time is hours per customer, or unit of time per customer. And the variance for the inter-arrival time is 1 over lambda squared. So exponential distribution is often selected to model interarrival times because it has this memoryless or no memory property. It is something like this. Suppose this is the last arrival, and then we are asking what is the interarrival time until the next arrival equals t plus h or more than that. Okay, but then we add the information, oh, we have passed the t units of time, and then we do not see any arrival. Now, this information, we can just ignore that because now we are here and we can just say, okay, I'm just calculating the probability of the next interarrival of the next arrival will happen at the time of h and more. Okay, so we do not need to keep track when the last arrival actually happens. It can be there, it can be actually there, there, or wherever. It doesn't matter because now we are here and then we just calculate. We are interested at h time units from here, so then we just calculate this. And then we ignore any information that has happened previously. So that is the memoryless property. So let's take a look at a bit of proof of the formula. So for the right-hand side here, probability A greater than H, we take the integral of the PDF of the exponential distribution starting from H to infinity. Here's the result. And then for the left-hand side, we use the Bayes theorem. And then here's the result. And then we look at this upper part here. The intersection between a greater than t plus h intersect with a greater than equals to t is a greater than t plus h. So here we have this. And then for the bottom part here, greater than or equals t, we simply have e to the power of minus lambda t. And then we put them all together here. So this is the upper part, and this is the lower part, and this is the right hand side. And then we see that when we simplify this thing, it becomes that, and that is exactly the same with probability of a greater than h. So as I said before, suppose we're told that there has been no arrival for the last t hours, and then the probability of no arrival during the next h hours is still p of a greater than h. So these things here, they're all equal. For example, what is probability that the inter-arrival time is greater than 9 hours, for example, given that 5 hours have passed without an arrival? This is the same with 7 and 3 because the difference is 4, 6 and 2. And these all things are equal to say, what is the probability that the inter-arrival is 4, which means that we will see an arrival in the next 4 hours. Okay, so it doesn't matter whether 5 hours have passed and then we're asking for 9 hours since the last arrival and so on. So the point is we do not need to keep track how long it has been since the last arrival. So if you just want to know what is the probability we will have an arrival in the next 4 hours, then just calculate that probability. It doesn't matter if the next 4 hours is we already spent 5 and then from 5 to 9 is another 4 hours, or we already spent here we already spent 3 hours and then the next 4 hours is up to 7. It doesn't matter. It is the same with saying what is the probability we will have an arrival in the next 4 hours. You may not be very impressed with exponential distribution or not very convinced about why we chose exponential distribution. So let's compare with discrete distribution. So let's say we use discrete distribution to describe the interarrival times. So, so here's an example. Suppose we know that the inter-arrival times is following discrete distribution. With the probability half, the inter-arrival time is exactly 5. And then with probability half, the inter-arrival time is exactly 100. Now, suppose that we know there has been no arrival in the last 6 hours. Then we know the next arrival must happen in 94 hours because it has been 6 hours past, so it cannot be this thing, right? It must be this 100 hours since the last arrival. So and the next arrival must happen in 94 hours. And then suppose we know there has been no arrival in the last 1 hour. Then we know for sure, because we're using this discrete distribution, the next arrival is equally likely to happen either the next 4 hours or the next 99 hours. So the main point here is that if we use discrete distribution, we need to keep track when is the last arrival, because we need that memory, we need that note to say what is probability of the next arrival will happen in t hours. So we need to know when is the last arrival. On the other hand, we saw that in the exponential distribution, we do not need to have that memory. We do not need to keep track when is the last arrival. We can simply say what is the probability there will be an arrival in the next 4 hours, in the next 6 hours, and then we can just calculate the probability regardless of when is the last arrival that has happened before. Okay, so now I hope you are quite impressed with the memoryless property of exponential distribution. Okay, so we've chosen exponential distribution to model the inter-arrival times. Now we are going to look at the relationship between exponential distribution and Poisson distribution. So the theorem here says that inter-arrival times are exponential if and only if the number of arrivals follows Poisson distribution. So inter-arrival times are exponential, time between the arrivals of customers, exponential, but the number of arrivals in a particular interval of time, number of arrivals, it follows a Poisson distribution. In other words, how many customers appear in an interval length of t follows a Poisson distribution. And here is the probability density function of Poisson distribution. So we can use this to calculate what is the probability during an interval of time with the length of t, we see n customers appear or arrive in the system. Okay, so inter-arrival time follow exponential distribution, but the arrivals, the customers that arrive, they follow the Poisson distribution. This is the relationship between them. And then the mean and the variance for this Poisson distribution, they are the same, which is lambda t. So the mean number of arrivals that occur in an interval length of t is lambda t. The arrivals that follow Poisson distribution also have assumptions. The first assumption is that the arrivals on non-overlapping time intervals, they're independent. So for example, the information about the number of arrivals between times 1 and 10 does not give us any information about the arrivals between times 30 and 50. The second assumption is that within a small time interval, from t to t plus delta t, the probability of having one arrival is lambda times delta t. The probability of no arrival in that time interval is 1 minus lambda delta t, and the probability of having more than one arrival is 0. If these two assumptions hold, then the number of arrivals within the time intervals t follows a Poisson distribution with parameter lambda t, and the interarrival times are exponential with parameter lambda. So the interarrival times are exponential. The number of arrivals within a time interval is Poisson. So here's what we've seen so far in the modeling of arrivals and the interarrival time. So for the interarrival time, we chose the exponential distribution with the parameter lambda, and lambda can be interpreted as the arrival rate, how many customers per hour. This is the probability density function, PDF. This is the mean of the interarrival time, and then this is the variance of the interarrival time. And then remember that the number of customers arrive in the system during the interval time small t follows the Poisson distribution. This is the PDF of the Poisson distribution. This is the PDF, and then this is the mean, and then this is the variance for NT, which is again the number of customers arriving in the system during the interval time T. So we are going to look at an example to practice all these formulas. So in this example, the important information from the first sentence is that the number of glasses of beer follows a Poisson distribution. It means that this glasses of beer is the customers here. Okay, so it has the average of 30 beers per hour. So if the number of customers follow Poisson distribution, we know that the inter-arrival time between the order for the beer follows exponential distribution. Okay, we will use that information to answer these three questions, and then there will be a pause in the video to give you some time to read this question. The first question asks, find the probability that exactly 60 beers are ordered between 10 p.m. and 12 midnight. So it's about the beers. And from the problem, we know that the number of glasses of beer follows a Poisson distribution. So here's the PDF of the Poisson distribution. So now we take a look at this notation here, and then we seek the values of those notations from the problem. So for this small n, this is 60. What is asked from the question? 60 beers, so that is the small n. And then we know that an average of 30 beers per hour being ordered, an average of, so this is like the arrival rate, 30 orders per hour, 30 beers per hour, 30 customers per hour. So that is our lambda arrival rate. And then the small t is this interval time here, so 2 hours. Make sure that you have the same unit. So if you use hour, then everything must be in hour. So we have all these values here. Now we can calculate the probability that 60 beers are ordered in the interval of 2 hours. Now the second question is still asking about something related to the number of beers. So we are going to still use the Poisson distribution. So it asks the mean and the standard deviation. So we use this formula. Later we will take care, because this is take care of this is variance and that is standard deviation. But in the meantime, we just use this lambda t, and then we ignore this 60 beers for this question, and then the lambda or the arrival rate is the same with the previous question, 30 beers per hour. Now the small t becomes 4 hours because it is between 9 p.m. to 1 a.m. Okay, so we plug in these values here. So we get the mean is 120 beers, and the standard deviation is the square root of that, which is 10.95 beers. Now the third one is a bit different because now it asks about the time between two consecutive orders. So we know that if we are talking about the time, inter-arrival time, then the distribution is the exponential distribution. Here's the exponential distribution, and then we are asked about the probability between 1 and 3 minutes. So we are going to look at that area. Okay. So we take the integral from 1 to 3, and this is the PDF, lambda e to the power of minus lambda t. But now you may notice that lambda becomes 0.5 because lambda was 30 beers per hour. Now we are talking about minutes. Okay, so we change this into minutes. 1 over 2 beers per minute. Okay, that's why you see here becomes 0.5 for lambda. Again, this is lambda times e minus lambda t. We take the integral, we plug in the value from 1 to 3, so and then we got the probability 0.38. Now let's talk about how we may model the service process. Again, for the same reason, we will choose exponential distribution to model the service time. And the notation is different. Now the service time is denoted by a random variable s. And then here's the density function. It is similar to the previous one, except that now we're using the mu instead of lambda to denote the parameter of this exponential distribution. And then we call this as the service rate. And same as before when we were talking about the rate, the unit is always customers per hour. Okay, and then 1 over lambda is the average service time. And the reason why we're choosing exponential distribution is again due to the memoryless property. And here's another example about why memoryless property is so great, because remember that we do not need to keep track when the last thing happened. Okay, in this case, we're going to see that we do not need to keep track when the last service finished. Okay, so we have 4 customers here, and the question is, what is probability that customer 4, the lady over here, will be the last of the 4 to complete the service? The answer is 1 over 3, because for this customer to complete the service, it means that it must be served to one of these server, this boxes here. So one of these 3 customers must have finished before customer 4. So any of them must have finished. Let's say customer 1, he has finished and then he leaves the system, and then customer 4 goes into that server. So now this is customer 4, this is customer 2, and customer 3. Due to the memoryless property, they have the same probability to finish the service. That's why the answer is 1 over 3. There are other probability distributions that people use quite commonly. Is the Erlang distribution. And then the parameters are k and k mu. And we can think of modeling the service time using this distribution is like breaking down the service time into k phases of service, and then each phase has a memoryless property. We may also use the deterministic service time, And then we can say if this is the case, then each customer service time is exactly 1 over mu. So to summarize, if we model the service time using exponential distribution, and then the parameter is mu, mu is called the service rate. Remember, when we're talking about the rate, the unit must be customers per hour, for example. So customer per time unit. And then here's the PDF, the mean, and the variance. They are all the same with the ones we have seen in the when we model the arrival process, except that we just changed the symbol from lambda to mu. So that concludes this video, and then in the next video I'm going to talk about the notations that we're going to use to describe a queuing system. So see you on the next one, and thank you.